All right, let's go over monohybrid genetics problems. Again, if you have any questions, let me know. I'm going to walk through this with you and hopefully help you to understand this a little bit better, okay? So this says, I'll go ahead and put my name here, just kind of to remind you about what we're doing here. I'm going to make this a little bit smaller, maybe even the smallest. Just like that. Okay, it says a black coat is dominant over white coat in guinea pigs. So this is dominant. So we'll call the alleles B's. So we know big B is dominant over little b. In order to have a white coat, you have to have two little b's. So we have a homozygous black pig. So homozygous meaning it has two of the same alleles. It's black, so they're both dominant. B is mated with another homozygous black pig. So again, the same alleles. What are the genotypes of the parents? Well, I just said that. So A, the genotypes are homozygous dominant. And what will be the genotypes, phenotypes, and probabilities of the first generation? Well, if we set up a Punnett square here, this is really easy. You could do this without setting up a Punnett square. But everything is dominant allele. So the probability, the genotypes would be 100% big B or homozygous dominant. Phenotypes would be 100% black. And probabilities of the first generation again would be 100% homozygous dominant for black. And then C, probability that white offspring will be produced. In order to have white offspring, you have to have two recessive alleles, and there are none, so that probability is 0%. Okay, let's move on to number 2. A heterozygous black pig. So heterozygous is big B, little b, but it's black, so it still has one dominant allele, is mated with a homozygous black pig. Homozygous black, two dominant alleles. What are the genotypes of the parents? Well, there they are. So that's A. Work the problem, show the possible genotypes and phenotypes of the offspring. So we're going to do big B, little b, big B, big B. We're going to make our Punnett square here. Okay, so our genotype, phenotype, we have 2/4 homozygous dominant and 2/4 heterozygous. So we have 50% or 2/4. Well, actually, sorry, 100% black. How do I know that? Because this, even though it has a recessive allele, it has one dominant, which masks the recessive. Okay, so now we're moving on to a black pig is mated with a white pig. The F1 generation, there are 5 black and 5 white pigs. First off, we know that, let me erase this stuff. So we know that if it's a white pig, it has to be little b, little b. It's the only way it can be white. And then the F1 generation has 5 black, 5 white pigs. So the black pig, in order to have any white pigs, it would also have to carry a recessive allele, because if it didn't carry a recessive allele and this was homozygous dominant, then we would end up with all offspring being heterozygous, so they would still be black. So this is the male pig that's black. Then it says give the genotypes of the parents. So there's the genotypes of the parents. This is the white pig, the black pig. Next, 2 heterozygous black pigs are mated. Show the genotypes, phenotypes, etc. So we have heterozygous black pigs times 2. Here we're going to have big B, big B, big B, little b, big B, little b, little b, little b. Genotype, phenotype, we have 1, so 1/4. Homozygous dominant, 2/4. Heterozygous, and 1/4 homozygous recessive. So these two are going to be black pigs because they each have a dominant allele. This one actually has 2. So we're going to have 3/4 black, and then the other 1/4 is white. Okay. All right. This says, so that was number 4. Number 5, in Holstein cattle, the spotting of the coat is recessive. So spotting of coat is recessive to solid color coat. So if it's spotted color, it's going to have to be, we'll say, little less, little less. What types of offspring might be produced from a cross of 2 spotted animals? So if they're spotted animals, again, they're recessive. So it would be little r in both of those. So we would have that times, again, this. Hang on just a second. All right. Sorry about that. So if they're both this, then the phenotypes are going to be, the genotypes are all going to be homozygous, recessive. Phenotypes are all going to be spotted. Okay. All right. So let's move on to this. Number 6. It says in peas, long stem A is dominant over short stem A. Give the expected genotypes, phenotypes, and probabilities for the following crosses. So homozygous long and short would be homozygous would be big A, mixed with little a, little a. So we'd set that up in a Punnett square. And we would end up with all heterozygotes. Okay, so the genotypes would be 100%, 100% heterozygous, and all long stem. Okay, heterozygous long and short. So we would have big A, little a, big A, okay, wait, hang on. So we have heterozygous long times a short. Okay, so if it's short, it has to be little a, little a. So we're going to go heterozygous, big A, little a, and then a short stem has to be recessive, homozygous recessive. So we're going to have a just like that. Then you can go ahead and do the genotypes, phenotypes, probabilities. So, I mean, I can tell you it'll be half heterozygous and half homozygous recessive. So the phenotypes will be half shorts, half long stem, half short stem. Okay, these will be the long stem, these will be the short stem. Next, we have heterozygous long, homozygous long. So again, anytime you see a homozygous long, you're going to know that everything is going to be the dominant trait. So if I have a heterozygous long and a homozygous long, again, I'm going to have homozygous, dominant, homozygous, dominant, and then these two will be heterozygous. So phenotype or genotypes will be 50% homozygous long, 50% heterozygous, and then you will end up with 100% long stems, okay? And last, heterozygous long, heterozygous long. So we'll do big A, little a, both heterozygous. So here we'll have all right, so genotype will be 1/4 homozygous long, 1/4 heterozygous, 1/4 homozygous recessive or short. So we'll have 3/4 or 75% long stem and 1/4 or 25% short stem. Okay. Number 7, a man with normal pigmentation is the dominant or is due to the dominant allele A. And albinism is the recessive allele A. So a normal man marries an albino woman. So, and they have an albino child. The only way they can have an albino child is if they get one allele, one recessive allele from their dad, one recessive from their mom. So even though this guy or man is normal pigmentation, he has to carry a recessive allele. So we're going to go big A, little a for the man, and then the mother was recessive because she was albino. So first child's albino. Only way that could be would be down here. And here. So it's asking what the genotypes of these three people are. Here's the father, mother, and child. Okay. All right, let me get off this and scroll down. All right. 8. An albino man marries a normally pigmented woman who had an albino mother. Okay, so if the mother was albino, she was R, or I'm sorry, we're doing A's here. Excuse me. So the mother had to be big A, or I'm sorry, little a, because she was albino. The woman is normally pigmented, so she has to get one of these from her mother, but she must have gotten a dominant allele from her father to make her normal. So this is the woman. And the male, it says, is albino. Okay, so this is the male. And then it's asking what are the possible genotypes, phenotypes of the children of this couple. So we have big A, little a, little a, little a. So again, you can see, I'll go ahead and finish this one out for you. So you're going to have 50% are heterozygous, so they will be normal, 50% homozygous recessive, so they will be albino. And there's that. Okay. Number 9. Deafness in a Cocker Spaniel is inherited. The allele for deafness is recessive to normal hearing. 2 Cocker Spaniels with normal hearing are mated together. They produce a litter of 8 pups, 2 of which are found to be deaf. So if they're deaf, the only way that normal breeding or normal hearing Cocker Spaniels mated together can form a deaf pup, if that is the recessive allele, is each of them have to be able, let's go with D's here, have to donate a recessive allele each to the pup. So they are both heterozygous. They are not deaf, but they each carry the allele for deafness. So it says give the genotypes of the parents. Here they are. Show the possible genotypes, phenotypes, probabilities of the offspring. So D. So we're going to have this combination. So the let's see here. The genotypes of the offspring are as follows: one homozygous recessive or homozygous dominant, one homozygous recessive, two heterozygotes. And then it's saying, okay, so phenotypes would be 3/4 normal, one deaf. How many of the puppies will be unable to produce deaf offspring? So how many of these pups will be unable to produce deaf offspring? Well, technically, they can produce deaf offspring if they're heterozygotes or homozygous recessive. Now, in order for this to produce a deaf offspring, it would have to marry another heterozygote or homozygous recessive. Okay, and then this would have to marry either one of these as well. So the only one that can't is the one that does not carry a allele for deafness. Okay. All right, last problem. Having dimples is dominant over not having dimples. A dimpled woman whose father had no dimples. So having dimples is dominant. So no dimples is not dominant. So this father was recessive. So the dimpled woman had to be heterozygous. Had to get one of those alleles from her father, but in order to have dimples, she had to get a dominant allele from her mother, and whose mother did have dimples. Okay, marries a man whose mother had no dimples. Okay, so mother had no dimples, so recessive. Whose father had no dimples, recessive. And whose grandparents on his father's side did not have dimples. This does not even matter. Doesn't matter. So we know that a man marries a man so if this man that she married, it doesn't tell us whether he had dimples or not, but if the mother had no dimples, father had no dimples, the man had no dimples. Okay? So genotypes of the man and woman are D for the woman, and homozygous recessive for the man. Show the cross, guys. You should be able to do this now. D, 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 D. So we're going to end up with two possible genotypes. Those will be heterozygotes here and there, and then homozygous recessive there and there. Okay. How many different phenotypes are possible? Again, two. Probability of getting DD offspring is 0. Probability of getting homozygous recessive offspring is half. So we'll just do 50%. Whoa, I don't know what happened there. But sorry, my screen's messed up here. All right, so again, you can go back and look at what you had, but the phenotypes are there we go. Sorry. I'm all messed up here. All right, sorry. So the genotypes, again, you can go back and look at my explanation earlier, are big D, little d, or heterozygous for the woman, and little d or homozygous recessive for the man. I showed the cross earlier. It was 50% this, 50% this. So two different genotypes possible. Two different phenotypes possible. 0% chance of getting homozygous dominant. 50% chance of homozygous recessive. Dimpled offspring, 50% chance. Remember, dimpled was dominant, so we had two heterozygotes. Probability of no dimples, 50%. And then probability of getting homozygous offspring was 50% with the homozygous recessive. All right, so I'm going to end the video there, and you guys are responsible for the following problems. You should be able to do these. Actually, this page goes with these. So all you have to do is follow along with what I did and fill out these as it goes. Okay, so that concludes everything that you need to know about this. So you should be able to complete this entire worksheet. If you have any questions, as always, just ask me.